Welcome to this explainer. Look, there's a massive fundamental shift happening in artificial intelligence right now. We're moving away from AI that merely talks about the world to AI that can actually understand, navigate, and act within it. This isn't just a software upgrade. This transition changes absolutely everything about how we build and interact with intelligent systems. Let's dive right in. So let's start with a kind of provocative question. If modern AI is so incredibly smart, why doesn't it intuitively understand how a glass falls off a table, right? I mean, large language models have this absolute linguistic brilliance. They can write poetry, code, summarize massive documents, but they have literally zero physical intuition. They don't actually know what gravity feels like or the consequences of glass hitting the floor. Think about it like the difference between memorizing a map and actually walking through a bustling city. Current AI knows the word glass is statistically associated with the words water, table, and gravity, but it doesn't experience the constraints of physical force. A map contains information, sure, but a world model contains actual, possible transitions. You know, it's fascinating how this totally mirrors biological evolution. Nervous systems didn't just start out with language. Hundreds of millions of years ago, organisms had to evolve vision, touch, and the ability to navigate physical environments just to survive. Language came way, way later as a tool for communication. So navigating physical reality, that's a far deeper, more foundational layer of intelligence than just speaking. Traditional AI operates in what we can call a prediction space. It's this flat, token-based representation of reality. You feed it inputs, text, pixels, audio, and the system just asks one basic thing. Based on statistics, what pattern comes next? But reality doesn't exist as a sequence of flat tokens. The physical world is made of objects, continuous forces, and spatial structures. And that fundamental limitation is driving a massive pivot in the field. Right now, most video AI just generates pixels. It creates a locally plausible next visual frame. Looks amazing, but if the camera turns, objects might literally disappear. The new paradigm we're shifting to is world construction. We're talking about systems generating persistent, interactive, three-dimensional environments. The underlying math actually remembers the world. This brings us to a critical conceptual threshold: spatial intelligence. A spatially intelligent system doesn't just recognize an object in an image. It maintains a persistent representation of space. It knows exactly where that object exists, how it relates to its surroundings, and what constraints limit its movement. It finally stops asking what pattern comes next and starts asking, wait, what state am I in? Okay, so to actually operate in this new state space, an AI needs a few non-negotiable ground rules. Objects need persistence, meaning they can't just vanish into thin air because the AI looked away. The geometry has to make sense. Walls don't randomly shift. And above all, there must be causal persistence. If an AI takes an action, it has to leave durable, lasting consequences in that environment. But building physical intelligence, it's kind of like climbing a ladder. Current spatial models nail the first two rungs, visual and geometric consistency, meaning things look right and stay put. But true physical intelligence requires dynamic consistency, where forces, motion, and friction actually work. And ultimately, you need operational consistency, where actions are tied to real costs and constraints. To reach that final level of operational consistency, we have to cross out of purely geometric models and into the energy landscape. We're not just in a 3D environment anymore. We're in a governable reality. It's a dynamic field that controls how a system transitions from one state to another based on stability, resources, and very real consequences. Which brings us to the energetic paradigm, or EP. This framework views intelligence as the ability to manage structured transitions within a constrained environment. EP is the critical layer that looks at an action and asks, sure, this works geometrically, but is it affordable? Is it reversible? Does it keep the whole system stable? Instead of hating you with a bunch of complex math, let's just break the EP equation down into human terms. A truly intelligent system weighs any action by asking some really practical questions. Does this actually advance my goal? What physical capacity or energy is being consumed? Could this destabilize the system? Am I losing my future recovery options? And are physical boundaries actually being respected? Let's ground this with a concrete example. Say an AI is commanding a robot to move a fragile glass to a sink. Under the energetic paradigm, it isn't just plotting the shortest geometric path. It is actively checking its grasp reliability, calculating collision risks with a table, anticipating the material fragility of the glass, and making sure there are recovery options if it slips. It's actively minimizing risk. Under this paradigm, a spatial world model becomes an active simulation decision loop. It's this incredible, low-cost experimental field. Candidate actions are estimated, simulated, put through that energetic evaluation we just talked about, and then either rejected or authorized. And all of this happens long before any real-world physical resources are ever committed. But there's a massive catch here, known as the reality gap. If you train an AI in a perfectly clean synthetic simulation, where friction is flawless and lighting never changes, it looks like an absolute genius. But throw it into the unpredictable messiness of the real world, that exact same AI can fail spectacularly. So, to prevent those spectacular failures, EP demands mandatory reality verification. When the AI takes a real action, it has to measure exactly where it went wrong. Was it a state estimation error, a geometric mismatch? Did the physics engine fail, or was it just clumsy motor control? By diagnosing the exact type of mistake, the system corrects only the specific layer that failed. This kind of structured error correction allows for a multi-scale control hierarchy. This is absolutely essential. High-level goal planning operates over hours. Motion paths happen in seconds. But contact control, like adjusting grip strength on that fragile glass, happens in milliseconds. EP ensures a high-level plan never ignores the immediate physical realities of millisecond-level contact. And that brings us to the ultimate destination of this explainer. This hierarchical integration of spatial intelligence and energetic evaluation culminates in a completely new architectural concept. We are officially entering the era of large energy models, or LEMs. This is the ultimate bridge between pure artificial reasoning and actual governable physical consequence in the real world. Now, there's a really important distinction to make here. A world model is fantastic. It maintains spatial states and predicts consequences, basically acting like a really complex simulator. But a large energy model goes so much further. It integrates that representation, but it actively governs the transitions, enforces physical constraints, and assigns authority based on real risk. So the complete evolutionary path of AI is becoming incredibly clear. We started with language models, mastering statistical relationships among symbols. Then world models, representing structured environments. Next was spatial intelligence, deeply understanding states and possible transitions. And finally, the pinnacle, large energy models, governing those transitions under strict physical objectives and feedback loops. Why does all this matter? Well, this transition carries immense human meaning. When AI shifts from just generating text on a screen to controlling real physical transitions, the stakes absolutely skyrocket. Our standards have to expand, demanding real accountability, because these systems are going to directly affect physical bodies, private property, and our civic infrastructure. I want to share this powerful thought from the source material. Intelligence is organized not around the next symbol, but around the preservation and transformation of structured reality. The next era of AI development isn't just about throwing more data at bigger language models. It's about building systems capable of understanding, navigating, and responsibly shaping our structured reality. As we step permanently out of the prediction space and fully into the physical world, the final question we really have to ask ourselves is this: are we ready to share our physical reality with systems that don't just predict the world, but have the intelligence and autonomy to actively shape it?